Hello students, welcome back. We just completed section 1, the rate of change. Here's a brief summary. Entire section 1 can be summarized by a single picture, a single static picture right here. Here the green lines are the secant lines, and the slope of secant line can be written as a Newton quotient like this, or as an average rate of change like this, or as a rise over run like this. And they're all the same, and upon taking the limit, we get a 0 over 0 type limit, and that's the instantaneous rate of change visualized by the slope of this red line, the tangent line. And we're going to use this limit to define the derivative, and using the derivative, we're going to define the derivative function. Here we go. The same instantaneous rate of change using the same average rate of change, or the same f prime of a using the same Newton quotient. They're the same as you saw before. Let h be b minus a, then b is a plus h, and then replace b here by a plus h, and b minus a down here by h. Then you're going to get this Newton quotient, so they're the same thing. So the first expression and second expression are identical, and that's how you define the derivative using the limit. And the visualization is, as you saw before, the slope of the tangent line, or the instantaneous rate of change. That's the derivative at a value right here. Now what if I change this a value? Change to some other place, then I'm going to get the slope of tangent line there. Change to some other place, then I'm going to get a slope of tangent line there. I'm going to get a function, a new function given by the derivative values. That function is called the derivative function. Here, replace a by x, and then x is moving around, then you're going to get the derivative function. Now, a little bit more notation issue. Most of the time, I'm going to use f prime of x or f prime of a, as you see in the left-hand side. That's French expression, introduced by Italian-French mathematician Lagrange. Sometimes, however, I'll use the right-hand side expression, dy over dx, and that's German expression, introduced by Leibniz. It's too late to change one to the other and just unify into a single expression. You know, mathematics was defined and developed in different places almost at the same time, and then they all claim that their own contribution is the best, you know. Talk to French people, talk to German people, talk to English people, they all say they are the best. And they all insist their own expression. Now it's too late to change anything. So you just have to learn everything there. Most of the time though, I'll try to use this French expression, prime expression. It's simpler, and whenever I use this, students do better. But dy dx notation, that's a little bit more intimidating, and students do not as well usually, but still, when it becomes necessary, I'll use it. Alright, so much for the definitions and the notations. But nothing will make sense unless you do some exercises. So let's go ahead and do that. Calculate the given derivative directly from the definition. Okay, here's an example. So what is f prime of 1? Okay, alright, here's a definition using Newton quotient. And I don't need color coding anymore, so let's go back to black. And let's expand the font a little bit. We want fraction here, so bigger font will be helpful. Finally, f prime of 1 is the quantity we are looking for, so let's replace 1 in place of a. There you go, that's the quantity we are looking for. Now, what is this f of 1 plus h? Well, 1 plus h will have to go here. So f of 1 plus h is, as a matter of fact, 1 plus h squared plus 1. Now, what is f of 1? Plug in x equals to 1 here. 1 squared plus 1, oh, f of 1 is 2. So that's the computation you have to do. Let's see. Is this a doable limit computation? Let's see. Let's copy and paste. 1 plus h squared. Well, if I expand it all, 1 plus 2h plus h squared, there goes the complete square, plus 1 and minus 2. Alright, that over h. That's a computation I have to do. Looks like this is not too bad. This 1 plus 1 minus 2, they all cancel out. And then we have a 0 over 0 type limit, as expected. And how do you calculate a 0 over 0 type limit? Let's factor it. Did I factor right? Oh, not yet. Okay. Factorization done. And then I can cancel out this h, that h. In short, I'm going to get 2 plus h, and that's 2 plus 0. Here we go. That's the computation. And that's the instantaneous rate of change at x equals to 1. That's the slope of tangent line at x equals to 1. Let's see. X squared plus 1, and then let's see, slope of tangent line at x equals to 1, so its slope is 2. Okay, I drew the curve f of x equals x squared plus 1. That's the blue curve. And at x equals to 1 right here, and slope is 2. Okay. Plotting is left to the students. Okay, there goes one example. Let's see, do we have time for another? Okay, we have another problem here. And previous problem was done through this Newton quotient expressions. So this time let's work out this expression here. Again, a little bit bigger font. And then I want G prime, and I don't want color coding anymore, so no color. And I want G of B over G of A, and A value is -1. So A value is -1. And B is approaching A, so B is approaching -1. Okay, that's the limit computation I have to do. Now, what is G of B? Well, right here, plug in x equal to B, then I'm going to get 3b squared plus b minus 2. Did I do this right? And then G prime, I want G prime of -1, so I want G of -1 here, plug in -1 here, what do you get? -1 squared, positive 1. So 3 minus 1, another minus 2, oh, this entire thing is 0. So G of -1 is 0. And then B minus of -1, so plus 1. Looks like this is a computation I have to do. Please check, did I do this computation right? G of -1 is 0. Okay, let's rewrite this. I don't need this 0. And is this a 0 over 0 type limit? Of course it is. Let's factor it. Denominator is okay. How about the numerator? Did I factor correctly? -2, +3. I think I did it right. So if I cross out the common factor, b plus 1, then I'm going to get 3b minus 2, no denominator anymore, so this is a trivial limit. Plug in b equals -1, so -3 minus 2, I'm getting -5. Is this right? Well, let's see, is this right? Yeah, -5 is right. By the way, how about the previous problem? Yes, +2 is right. Well, okay, they're both right. And there's no reason to keep those here, so let me just go ahead and open up the answer keys. So Newton quotient and simplify. We have a 0 over 0 type limit. Do your computation. Or you can use the average rate of change formula too. F of b minus f of a. Here a is 1. And then simplify. Again, you get 0 over 0 type limit. Factor and simplify. Once you get the trivial limit, plug in and do your computation. Either way, you get the same thing. We do the same thing for the second problem. We can use Newton quotient like this. And then, once you get 0 over 0 type limit, factor and simplify, and then use the trivial limit rule, plug in. Or we can do average rate of change computation, what we just did. Factor, simplify, and then plug in. So we went through a couple of exercise problems, and we used both expressions, Newton quotient method or average rate of change method, either way. Which method do you like better? Well, if you said neither, then you are one of those 99% of the people. We're going to learn much easier methods pretty soon, but please be patient. Let's take care of some terminologies here and there before moving on to the derivative function and how to calculate the derivative function. This derivative computation is calculating the derivative directly using this average rate of change through calculating the instantaneous rate of change through average rate of change, or the derivative through the Newton quotient, either way. But it's not the most efficient way to tell the truth. The most efficient way is to calculate the derivative function and plug in x equals 1 or x equal to -1. How do you find out the derivative function? Well, that requires some formulas and tricks, and that's something we're going to start shortly. Let's come back and discuss that in a moment. Stay tuned.